1. Okay, and we're recording. Hello, YouTube. You can see I've decided to try to make this marginally more visually interesting by having a little me in the corner. Hello, YouTube. It is me in the corner. Okay. So as you can also see, this is I will give in to my irresistible urge to mug for the camera all the time now. Sorry, not sorry, I guess. Anyway, we still have our usual rules. Let's see. So the reading for today is 8.3 and 8.4, and we will go over sections 8.3 and 8.4 today. And Wednesday we'll finish up chapter 8, and then maybe actually get onto chapter 9 in a little bit. But of course, this is probably not your immediate concern, because your immediate concern is probably there's both problem set 9, which is in principle due today, but in practice, oh dear. Hang on 1 second. Everything has decided to make a noise right now. I'm just gonna let that go. This is life during quarantine. Like, all the noises will go off all the time and are captured to YouTube. Sorry about that. Sorry, I should have turned off my phone. Even during video lecture in quarantine, there's still class interrupted by somebody's cell phone. Right, well, that's my own, so it's my fault. Okay, so what was I saying? Sorry, I so rudely interrupted myself. Oh yes, your immediate concern is probably our second exam, which is 1 week from today. And so let me just check. Has everybody gotten? So I emailed the review sheets, the sort of study guide, and the sample exam to you over the weekend. Did everybody get that? Say yes in the chat box. Okay, good. And that same stuff is also posted on our webpage. So it's all there. Oops. I don't. Well, okay. So let me cross out this now contradictory bit. So the exam 2 will no longer be on Wednesday, April 22nd. It'll be on Monday, April 27th. This is the correct date. We are going to try to use that same exam procedure that we did last time. It'll be done on paper, submitted by Canvas, and proctored by Zoom. And we will do one more rehearsal but in the last 5 minutes of class today, when everyone's going to turn on their cameras and write a few things on pieces of paper. There'll be different things from last time, but again, it'll be the last 5 minutes of class. So I hope everybody's ready for the exam rehearsal. Just say yes in the chat. You're listening to the smooth sounds of IAA, Industrial and Applied Algebra. Okay. AIA, Applied and Industrial. Yes, I'm going to try to do math ASMR. That's right. Okay, so let's proceed. And hopefully there as many people as possible will drop in and at least by the end of class today, because we're gonna, that exam rehearsal is worth 5 points, homework points. It's not a huge amount, but it's not 0. And so, because I really want to make sure that everybody's able to do this. And if you're not able to do this for some reason, I want to be able to talk to you about it as soon as possible. So, okay, so if there's some problem, some technical issue or other issue that makes it difficult for you to participate in this sort of online exam submission thing, well, let me know, and we'll figure something out. I mean, we really are all in this together. Okay, as much as I can make it. All right, so let's zoom back in and pick up where we left off. Where did we leave off? Yes, right. We were talking about. So remember, we're talking about cyclic codes. Actually, I should probably put in a little bit more reminder stuff here. We're talking about cyclic codes. So remember, cyclic codes are invariant. That is, they don't. You take code words to code words under cyclic permutation of coordinates. So So that's what they look like as sort of ordinary code words. And it's not obvious that those would somehow be more interesting than any other code words. Like, what cares? Who cares if you like rotate the coordinates and you send code words to code words? Well, so what? I don't see the big deal. But as it turns out, those codes are somehow better than, well, not necessarily better than others, but they're more, they can study them using algebra for the following reason, which we mentioned last time. So if C is a cyclic code of length n over FQ, oops, and I think starting today, and I realize I think I have to go back and revise chapter 8 to make it simpler. So I'm going to actually, I apologize to those of you who have really gotten into chapter 8, but I'm going to go back and fix up chapter 8 so it's so that I take out some extra stuff and leave make it as straightforward as possible, which is still not easy. So here I just want you to think that Q equals 2. I think this slide is the last time Q appears today. Anyway, so if C is a cyclic code of length n over F2, then the idea is that C is an ideal of R, which is F2 bracket X. Let me just replace that. So this is supposed to be F2 bracket X. So polynomials with coefficients mod 2, mod X to the n minus 1, setting X to the n equal to 1. But the point is that cyclic codes of length n are ideals of this ring R. F2 bracket X mod X to the n minus 1. And which for many purposes you can just think of as polynomial. It's just all every once in a while you have to reset X to the n to be 1. So in fact, not only are these is a cyclic code an ideal, it's a principal ideal of the following sort. It's generated by some g of x that divides x to the n minus 1 as a polynomial over F2. So we can study all cyclic codes of length n by factoring. I mean, this is actually true for general cyclic codes, and this is, if you get into coding theory, this is sort of what you do for a living. This sort of thing you do for a living. But just in terms of making money, even we can sort of list every single cyclic code of length n by looking at the single polynomial x to the n minus 1 and factoring those that polynomial. So and the sort of upshot of this, so one kind of cosmic upshot of this, spiritual upshot of this, is that cyclic codes are natural objects found in nature. So in a way, I mean, in a way that's bad because you can't sort of make them up and have them be however you want. I mean, and that actually tends to be sort of true of all, oddly enough, of all good codes. But okay, but here in particular, cyclic codes are objects found in nature, and so you can't sort of bend them to your will. I mean, the universe is the way it is. Cyclic codes are the way the cyclic codes out there are just out there to be waiting to be found. On the other hand, they're out there waiting to be found, and so you can, and so in a way that makes it easier because you just go get them. And we'll start to see, I hope by the end of the day, we'll start to see some circumstances where just the same things just keep popping up because, well, there's only so many things out there in nature to be found. And so there we go. All right, anyway, so the theorem that we got to last time and sort of the details of this, well, okay, we'll actually see those details a little bit later today. But suppose we have, let script C be a cyclic code of length n over F2. Like I said, Q is always going to be 2. So then, and with generator g of x, so remember, so C is the set of all polynomial multiples of some fixed polynomial g of x with coefficients mod 2, and that polynomial has to divide x to the n minus 1. So, once you have that, once you've set that standard, then you can actually compute. Once you know the degree of that of the generator polynomial, you can actually compute the dimension of your cyclic code. The important thing is that the bigger your degree, of your generator g of x, the smaller your dimension is. So what this formula, I mean, it gives you a precise formula. The dimension of your code, the amount of data that you can carry is k equals n, the length of your code, minus the degree of your polynomial. So what this says, I think I'll say this. I'm sure I'll repeat this later on, but repetition is the mother of belief. Repetition is the mother of belief. Repetition is the mother of belief. So well there. So we prefer G of smaller degree because if we have a generator polynomial G with a smaller degree, then that code can sort of carry more data bits per transmitted bits. Remember, because you want to remember that our framework is exactly that. So n is equal to the number of bits that you transmit when you use a particular code, and k is the number of information bits contained in each code word. And so, for a given n, you would really rather have more information bits. So one of the sort of main sort of money-making content of that theorem we talked about last time, and that you have to prove in problem set 9. Okay, so like I said, the problems from problem set 8 from chapter 8 are maybe not exactly your immediate concern. You can sort of maybe finish them later, but still, the thing I want that you need to sort of take away from that to continue from what we're discussing today is that because you can determine the dimension of your code from the length of your code and the degree of the generator polynomial, it follows that you really want to have a G with as small a degree as possible if you want to carry more information in your code words. So are there any questions about this so far? This is where we ended up last time. That was too small. Okay, and I think no questions in the chat. Okay, so we'll soldier on. And I think, but I think if any of you, if your question is like, what is this all about? Maybe I think that'll be better answered by the examples that we'll see. All right, so just so you know, just as I mean, I think because actually the nitty-gritty details of cyclic codes are even harder than the theory, we're actually going to sort of study cyclic code at kind of a 30,000-foot viewpoint, kind of more on a sort of almost like a hypothetical scale, but on a sort of big picture scale at least. But I just want to assure you that there are at least there exist practical ways of encoding and reading cyclic code. So just so you know, if you want to encode, here's one way to encode and decode cyclic codes. So if you have, remember, oh yes, I forgot to copy over initial setup. So script C is a cyclic code of length n. Oops. Length n, and G of x is our generator. And that generator has degree r. And remember, we just saw that point. The point is that the main point of what we just saw is that the dimension of the code, the amount of information the code can actually carry per code word, is n minus r. It's the length of your code minus the degree of your polynomial g. Okay, so in order to encode k data bits, let's say number them m0 through m sub n minus r minus 1, or I guess I should have said just m sub k, or m sub k minus 1. We write m in polynomial notation like so, and so the thing that we transmit is exactly the code word, just m times g. So at least that's one way of thinking about it. And so no information is lost because so there's no way we're actually going to erase the bits m. Yeah. So this is so just by distributive law, this is m0 times g of x plus m1x times g of x. So this is mildly complicated because it's multiplication of polynomials, but at the very least we don't lose any information because each of these we don't lose anything from these bits m0, m1 up through m sub n r minus 1. I just want to observe that no information is lost because each of these vectors we saw. Oh yeah, that is the one thing we actually want to get into the details of this theorem, which and this is the interesting part that you will prove. Oh no, that's actually the part that I proved last time, or the proof is in the book. These vectors are linearly independent, and so no information is lost because those vectors, having no information lost is exactly the same thing as saying that these vectors are linearly independent. Whoa, this is the point of linear dependence. That you can somehow extract these information. You should be able to extract these information bits from this expression. So encoding involves polynomial multiplication, and so it will. And so if there are no errors in the middle, though of course dealing with errors in the middle is sort of the main point of what we're all doing. But if you happen to be in the case where there are no errors in the middle, then in order to decode the code word that you receive, well, you divide. If encoding is multiplication, then decoding is division, and so in order to get back the message that you intended to send, you just divide by g of x. Yeah, and so if g of x is not if g of x does not divide y of x, you might wonder, like, well, is there some sort of remainder here and not an exact quotient, an exact polynomial quotient? Well, if g doesn't divide y, then y is not an element of the code, and something must have happened. So at least this is already an error detecting scheme. And I guess so. Remember, I just want to point out here that the hard part is not necessarily decoding, sort of to read a received word, code word. The hard part is error correction, which we will skip. Oops. Quite enough. There. Yeah, so the hard part of it, remember, is error correction, but and there's actually a really cool algebra that goes with that, but it's sort of above and beyond what the scope of this course, and so we won't deal with it. Okay, but that's that. But just and I think even the details of this page, I think I will not require you to know, but I just want to assert to you, I want to describe to you the fact that there is some way of encoding. I mean, so remember our sort of our setup before, where we had remember we have Xavier. Xavier has a message that he wants to send, and so he encodes that into a code word, and that's sort of this stage here, the encoded bit. Then there's a transmission. Maybe some mistakes happen in the middle, and then Yolanda, the receiver, decodes, maybe hopefully corrects those mistakes, that part we're skipping, and then decodes the hopefully correctly received code word, at least corrected code word, into the original message. And so we've eliminated somewhat the encoding part and the decoding part and the sort of reading part, but the part we were missing is the error correction. And like I said, that's beyond us in this course. That's for like the maybe 3 courses after this. This is really this is when you take all the sort of proofy abstract algebra and then apply those proof skills that you pick up to making money, which there is money to be made there. Okay, but for now, are there any questions about how to encode in a cyclic code and how to read in a cyclic code? See, this is Hello, YouTube. This is now the new visual interest of these videos, is you get to watch me sip water every now and then. All right, so let me do an example. Okay, so again, these are all over F2, and actually from now on, all of our codes will be over F2. And I had some leftover stuff when we talked about FQ, but I think it's which actually is important. We'll actually sort of be able to. We're actually going to use FQ later in order to construct codes. Actually, we'll do that momentarily. But the codes themselves will be over F2. Anyway, so over when we have coefficients mod 2, we remember that x to the n minus 1 is equal to x to the n plus 1, and it factors like this: 1 plus x times this, which you can sort of check that if you multiply these out, you get x to the n plus 1, because a bunch of stuff cancels out in the middle. So let's look at the cyclic code generated by x plus 1. So these so the question is what? Oh, no, that's not the question. The question is, can I make this nice and wide? Oops, actually, let me blow this up, which I think will mess up what I just did. Yeah, there we go. All right, so let me make this nice and wide again. So what do the code words, corresponding code words, look like? These are all of the polynomial multiples of x plus 1, which is actually the same thing as x minus 1. Because we're working mod 2 and plus equals minus. Which are, right, so how's this go again? Oh, right, it's the factor theorem. The factor theorem says that if you have a multiple of x minus 1, that you have a polynomial that's divisible by x minus 1, those are all of the polynomials of length at most n minus 1, f of x of degree at most n minus 1, of degree less than or equal to n minus 1, such that, well, these are all of the degree less than or equal to n minus 1 polynomial multiples of this one particular polynomial, which are all the polynomials degree at such degree less than or equal to n minus 1, such that f of 1 equals 0. Because remember, this is the factor theorem. Oh, the factor theorem! Remember that from high school, or from like a month or two ago? Well, like a month or two ago, that was like 10 million years ago. I know. I mean, in a normal semester, a month or two ago was 10 million years ago. But certainly this, certainly this semester, a month or two ago is like 10 bazillion years ago. Anyway, so if you may remember, x minus 1 divides a polynomial. A polynomial f of x is a multiple of x minus 1, exactly when f of 1 equals 0. So period. But f of 1 equals 0 exactly when the sum, but f of 1 is the sum of the coefficients of f. Right? So if you take a polynomial and you plug 1 into it, then where you're getting is the sum of the coefficients of f of x. So so the code words of C are exactly the code words whose coefficients sum to 0, i.e., this is the parity check code. What? Yeah, it's the parity check code. This C is the parity check code of length n. Okay, so let me draw a little picture of this. So remember, so let me remind you what the okay, so this is going to look like C0, length n is going to look like C0, C1 up through Cn minus 1. And remember, that corresponds to, in its polynomial representation, looks like f of x equals C0 plus C1 x to the 1 summed up through Cn minus 1 x to the n minus 1. Oops, that was a little bit messy there. Let me fix that again. Actually, it's all kind of messy. Whee. All right, so let's try that again. C0 plus C1 x to the 1 summed up through C sub n minus 1 x to the n minus 1. So remember, these are all the polynomials of degree less than or equal to n minus 1. I mean, it could be less than n minus 1 because if some of these higher coefficients are equal to 0. Anyway, so this is both the sort of usual vector representation of such a code word, and over here is the polynomial representation of such a code word. So we have that correspondence there, and when do we so when does that vector actually represent a code word? So in the parity check code, oops. So in the parity check code, let me remind you, the parity check code is the code words. Oops. The parity check code is all of the vectors of this form with. So remember, what determines a vector to being in the parity check code is that the sum of all its coordinates, C0 through Cn minus 1, is equal to 0, right? And you can think of, you can think of this particular coordinate 0 as the parity check code, as the parity check. You can remember if you have information bits. If you have information bits C1 through Cn minus 1, then the way to make that into a parity check code word is that you add on C0 by letting C0 be the sum of all the other bits. Well, some being plus or minus the same thing, sum, difference, whatever. It's all the same thing. Mod 2. So remember, the parity check code of length n is obtained in this fashion. It's all the code words of length n where that sum to 0, and on the other hand, in the polynomial form, we have all of the polynomials f of x of degree at most n minus 1, where f of 1 equals 0, and that again that happens exactly when the coefficients are equal to the sum of the coefficients equal to 0, i.e. a multiple of x plus 1. Okay, so yeah, so as it turns out, oh yeah, sorry, I forgot to say the whole point of my doing these. So I'm going to go through a bunch of examples, and one of the things that we're going to see in the examples is that every example that we've looked at so far is going to turn out to be a cyclic code. That's right. That was my point of that. So we see so far we see that 1 plus x is divisor of x to the n minus 1, which is here the same thing as x to the n plus 1. And there should be a cyclic code that corresponds to that. And in fact, that cyclic code is the parity check code of length n. So any questions about that example? So looking back, it seems that one of the very first examples we looked at just happens to be a cyclic code. So good so far? Say yes or ask a question, please, in the chat. Okay, yeah, this is, I mean, you know, this is some deep stuff. So, I mean, it's a deep stuff because it's actually it comes pretty close to like things that you would actually use to make money, things you would actually use for a living if you're going to use codes for a living. Okay, here's sort of the opposite. You may, well, there's this other fact. Here's this other factor of x to the n minus 1, which is equal to x to the n plus 1. What happens if we use the other factor? So this is the sum of 1 plus x plus up through x to the n minus 1. So what is the cyclic code generated by that thing? Using this, there is only, because this has degree, so let me start talking and writing. Because our generator g of x, and actually I didn't actually say what g of x was, so let me say what g of x. In case you hadn't guessed, this is g of x. So because our generator g of x has degree n minus 1, the only polynomial multiples of g of x with degree at most n minus 1. Well, at most n minus 1. Well, the only way you can get you can multiply that by some polynomial and get a polynomial of degree at most n minus 1. Degree of most n minus 1 are 0 times g of x and 1 times g of x. You have to multiply by a constant polynomial, because if you multiply by a polynomial of any larger degree, you get something of degree at least n. So the only code words in the corresponding cyclic code C, corresponding cyclic code script C, well, okay, C, but script C, think, are exactly the zero code word and g of x itself. So so the zero in polynomial form. So now you get to see me do the forbidden action of touching my face. Oh no! So I think you all know what the zero polynomial corresponds to, or you might have some idea, or at least it won't. I think it won't surprise you to see that the zero polynomial corresponds to the code word, the vector with all zeros. What's g of x? So remember, so this is as length n, and remember the coordinates here that we're choosing correspond to c0 all the way down to c sub n minus 1. And so if we the coefficient, if we look at this polynomial g of x, well, the c sub 0, well, all of its coefficients from the zero place to the n minus 1 place all are all equal to 1, and so this is exactly the all ones vector. So the code script C, it contains exactly 2 code words, the all zeros vector and the all ones vector. All right, so I would understand if nobody remembered the answer to the following question, but it is it is the sort of thing that it's actually a good exam review. This is a sort of thing that might show up on the exam, the use of this example, the knowledge of this example. So does anyone remember the name of this code that has exactly 2 code words in it like this? The all zeros vector and the all ones vector. Yes, excellent. So this is the, thank you, Ryusei. Fantastic. Great. So yes, so C is the repetition code of length n. So C is the repetition code of length n. Well, okay, not that surprising. Yeah, so it turns out that this one factorization, which works for every length n, happens to be the example of the two examples that we saw that work for as codes of every length, the parity check code and the repetition code. So again, see, it just happens. I mean, so there's only one example of codes that we haven't seen, or essentially one example of a code that we haven't seen yet. So yes, that's coming up. But are there any questions about as to why this factor of x to the n minus 1 gives you the parity check code, and this factor of x to the n minus 1 gives you the repetition code? Okay, fantastic. The repetition code. Okay, and did I? Oh yeah. So right now, then I'm making a. Oh yeah. So this here. Let me just make an observation about dimension here. Here the dimension. Here the degree of G is 1, and the dimension of C is n minus 1. As you expect for the repetition code of length n. You just lose one dimension, and so you're able to transmit a lot of data, n minus 1 data bits, but at the cost of you can't really correct anything. There's no error correction. Here we have lots of error correction. Here we have the degree of G is n minus 1, and so the dimension of your corresponding code is 1. The all ones vector is a basis. The set containing just the all ones vector is a basis for our code. So here, as you may remember, with repetition code, you can actually correct a lot of errors. Remember, you can correct basically. It's basically n minus 1 over 2 errors, but it's the floor of that. Because you have to round down that number of errors. So here again, because you can look at it this way, because G has a relatively high degree. This gives you a code that corrects lots of errors, but has a very low dimension. Okay, and so right. And so here's one last example. Here we have length 7, and so length 7. I mean, there's only sort of basically one other code that we looked at. So, this is going to be length 7. So I hope you sort of have some idea what's coming. But anyway, let's see. So length 7. So you can factor x to the 7 minus 1 in this very special way. It's x plus 1 times 1 plus x cubed plus times 1 plus x squared plus x cubed. So if you multiply all this stuff out somehow and take coefficients mod 2, somehow this actually comes out to x to the 7th plus 1. That's just the way the universe works. And let's look at the cyclic code generated by 1 plus x cubed. And let me so this is not as easy to think about as not as straightforward to think about as the other ones. So let me at least talk about the dimension. The dimension is going to be 7 minus the degree of G, which is 3. So this is a 4-dimensional code. And a basis, as we were saying in that theorem, a basis for our cyclic code C is the columns of the following matrix. of the following matrix. So let me, remember it's going to be, so it's 1 plus x plus 0x squared plus x cubed. So let me remind you about how to again, let me remind you again how to turn polynomials into vectors. This is the ones place, the x place coefficient, the x squared coefficient, and the x cubed coefficient. Right, so that's the polynomial 1 plus x cubed written out as a vector. But remember, this is length 7, so we have to go to x to the 4th, x to the 5th, x to the 6th. And so there's 3 more zeros to go. And remember, when we take a basis for that cyclic code, oops, I hope I didn't make everybody motion sick just now. You have your generator, then x times the generator, and then x squared times the generator. In other words, you take the generator and you start rotating it. You start permuting it cyclically. So we move it down 1, 1, 1, 0, 1, and then we move it down again 1, 1, 0, 1. Now we've reached this last one coordinate lines up with x to the 5th, and we move it down one more time 1, 1, 0, 1. That last coordinate lines up with x to the 6th. And so let me fill in the zeros in different colors so they're a little easier to see. No, it's not the color I intended, but that's fine. There. Actually, let me change the color of these guys, because color coordination is what separates us from the lower animals. Anybody see Steel Magnolias? Great movie, Steel Magnolias. There we go. All right, so so the theorem that you and I proved together, I proved the linearly independent part, and you're going to prove the spanning part in your homework. Shows that these four vectors are a basis for the cyclic code C generated by this polynomial, and now something very non-obvious happens that I won't really explain. It turns out that if we after a change of coordinates, this code is equivalent to well, essentially the only other code that we know. This code is equivalent to the Hamming code of length 7. That's not obvious at all, but it's true. So if you sort of switch the coordinates around a bit, then you get the Hamming code of length 7. And the point is, so all the codes we've seen so far are cyclic. And it is often the case. I mean, this is sort of a general, a particular instance of a kind of a general principle. It works pretty often. That in general, better codes are often symmetric in some way, and vice versa. And symmetric codes are often sort of better in some way, and vice versa. Or at the very least, they're somehow more comprehensible for human beings to study. And so, well, I don't know. I mean, it's hard to say how good codes are that we can't understand, because we can't understand them. So, at least in terms of what human beings seem to be good at, or at least human beings who like algebra are good at, this seems to be true. Okay, so yeah, my daughter's saying hi. My daughter's saying bye. She corrects me. Okay, so right. So cyclic codes, it seems, are everywhere. Or at least are everywhere in the examples that we have studied. So any questions so far? All right. So I think now, yeah. So okay, I want to state our motivating problem. Oops, there we go. So now we have, yeah, so let me set up our motivating problem, and then I'm going to ask you to sort of at least get ready to do our upload, our second upload rehearsal. So now we have a new way to discover codes in nature. So and the problem is given F2, I guess I should say. So again, we're no longer, I've abandoned this fancy idea of doing cyclic codes over arbitrary fields. Now we're going to do just F2. So I want to be able to choose an n, a length little n, and a g of x that divides x to the n minus 1, so that the cyclic code, the corresponding cyclic code, has both a relatively large dimension and a large minimum distance. So in order, and there's a tension between these two things. There we go, tension. So is it, you have one thing pulling one way and another thing pulling another way, and the question is, can you actually sort of somehow make them meet in the middle? Look, visual interest. There we go. I'm like pulling my two hands into each other. So on the one hand, we would like a large dimension. So in other words, we want to find a g of x with a small degree. So in our example of this is the parity check code. Parity check code, we had the degree of g of x is 1. That was good. So we want g of x to have a small degree because the dimension of your code is n minus the degree of your generator. On the other hand, in order to get, we also like a large minimum distance. So there we had example. We had the repetition code. Which has a minimum distance. Remember, the minimum distance is the smallest possible number of ones in a non-zero code word, and there we had minimum distance n. Yeah, minimum distance n. That's right. Yeah, not n minus 1, but n. Okay, and so here the minimum distance. The minimum distance can't be any bigger than the degree of our generator. So we definitely don't want R to be too small. So I guess this is one of those things when you deal with nature. There's always going to be this balance, but you want to have a small enough degree g, so that you actually carry a lot of information in any given code word, but you want a large enough degree g to try to get a big minimum distance. So that's tough. That's not obvious. All right, so again, we want to find generators that give you a corresponding cyclic code with a relatively large dimension. Actually, this is like a thing people do, right? Underline things. We want a large dimension, but also a large minimum distance, because that's a money-making code. That will somehow allow you to transmit a lot of data in an efficient way, sort of, not without inflating too much and slowing down your transmission rate too much, but with a large minimum distance, which will give you a large amount of error correction. So that's hard, and that's why people do this their entire lives. Okay, so in the rest of today, the remaining 20 minutes of talking, and on Wednesday and subsequently, we'll talk about one way to, I guess finishing up on Wednesday, we'll talk about one way to do that. But right now, what I want you to do is to prepare for our exam upload rehearsal, which means that if you're not already, so we'll take a minute here. I'll maybe have another sip of water. You should please log into Canvas if you haven't already, and there should be. And I want you to connect to Zoom with something with anything that has a working camera. It could be your laptop. I mean, I'll stop recording before I have everybody turn on their cameras. But in the last 5 minutes of class, we will have the cameras on. And I want you to get two separate pieces of paper ready. And remember, I want you to write on only one side of each piece of paper, because scanning seems to not work very well if you write on both sides of the paper. So I'll take a few seconds and let you do that. Or we'll just start that, and you can just sort of keep going as I lecture some more. Okay, so I hope everybody's at least starting to do that. How many people are here? There are now 20 people here. Well, okay, all 20 of you. Hopefully more people will show up at the end. I mean, it's by the way, this is okay if you're not. I mean, I'm going to admit, I hope this has been clear. But let me state this openly. That's okay if you're not here and you watch this on YouTube later. And yeah, but don't turn your camera on now because it'll show up. Anyway, yeah, there we go. Okay, right. So some of you at least have your cameras ready. Yeah, so it's okay if you're only watching this on YouTube. Hello, YouTube. But I hope everybody will be here for the last 5 minutes so we can really test this out and not have 1 week from today be the first time that we actually test this out. Okay, so let's continue talking. So I want to talk about field extensions. So an extension of a field, an extension. Oops, it's annoying. This not scribble that out. An extension of a field F is a field E that contains F as a subfield. So in a finite extension field of F2 as an extension E of F2 that is itself finite. So I guess this we don't really need this term here for this special case, but for a sort of more general version of what we're about to discuss, it's important to talk about field extensions in general. But it's enough here to think about. Okay, so we have some big fields. These are the E's. We have E is your big field. Actually, I should just type this out. So the picture you want to have in mind here is you want E to be your big field, your extension field, and that each of those contains a little field F2. And remember the reason why, for example, the reason why we know that F8 contains a little copy of F2 is that, for example, the way that we construct F8, as we saw, I hope we saw from the homework, as I'll remind you momentarily, F8 is obtained by taking polynomials with coefficients in F2 and modding up by the single polynomial x cubed plus x plus 1. That polynomial sounds familiar. All right, anyway. You'll see you'll see this all. It all comes back to the Hamming code. Anyway, so remember that F8 is constructed by taking F2 bracket x and modding out by x cubed plus x plus 1. And so therefore it contains a little copy of F2 inside it because the coefficients are all mod 2. Okay, so that is the picture that you want to keep in mind throughout this this section and the next. There's always a big field and a little field. There's a big field and sort of a smaller base field. And for us in this class, the base field will always be F2. Okay, so now but sort of again saying in general, just to introduce some terminology in general. Suppose big E is an extension of big F, and little f is a polynomial with coefficients in big F. To factor over big F means you factor f as a product of two polynomials with coefficients in big F, and factoring over the bigger field big E means you factor f, you write f as a product of two polynomials with coefficients in the bigger field. So what do I mean by that? Well, so it's important to keep that distinction between what happens in the little field versus the big field, because x, for example, here's a sort of relatively familiar example to keep in mind. X squared plus 1 is irreducible as a polynomial over the reals. So this is sort of our little field f. But factors as x plus I times x minus I over the big field of the complex numbers, which we think of as our E. So remember, so the point is that when you, hey, if there's a point to this, maybe I should type out what the point is. The point is when you make the field, the coefficient field bigger, you can often factor polynomials further. You can factor them into smaller pieces. And so, as we'll see, the sort of the technique that we'll use to come up with good polynomials to use as generators for cyclic codes is we're going to actually sort of construct them using a big field, using sort of complicated coefficients, and then magically be able to choose the big products of big coefficients so that that they all come out over sort of the ground field F2. Well, okay, that was super vague, but you'll see. I think by the end of today you'll see something about what that means. All right, so let me talk about the motivation for this. Right. So let me zoom out so I can show you this. So now this whole slide at the same time. So this theorem, this is called the BCH theorem, says that suppose C is a cyclic code of length n and with a generator G in the usual way, and suppose we have some fixed positive integer delta, and I should give a name for this because it's slightly prejudicial, but it sort of explains what the point of this is. So delta is the apparent, is what's called the apparent. Delta is the apparent minimum distance. That's the right term. Which is explained over here. So suppose you happen to have some positive integer delta and some alpha in the big field, capital E, where just so happens that the order of alpha is exactly equal to n. In that case, we have and that and I left out the word and here somewhere, and we have that that alpha and alpha squared and alpha cubed all the way up to alpha to the delta minus 1. These are all roots of G. That if you plug them into the polynomial G, then you get 0. So in that case, if we can somehow come up with that magical circumstance, then the minimum distance D of the code C is at least delta. So that's why delta is called the apparent minimum distance of the code C. It's because we know that the minimum distance will at least be at least delta. So this is somehow, this BCH theorem gives us a scheme, and there actually are not a lot of these schemes in existence. Like if you could come up with some scheme like this, you could make a whole lot of money. You could make a whole lot of money if you come up with some scheme that worked like more than once. I mean, forget working like up to infinity. If you just had some scheme like this work more than once, then you could make a boatload of money. Anyway, so the point is, if we want to find a good code to find for the purpose, so to find a good cyclic code, we want to solve the following problem. So let E be an extension of F2. Basically, let E be a finite field of E of order 2 to the E, 2 to the little e. And suppose alpha is a non-zero element of E, in order of the multiplicative group of E that has order exactly n. So the goal is to find a G of X of smallest possible degree, so as small as possible polynomial with coefficients in F2, such that G of X divides X minus X to the n minus 1, and all these things are true. So remember that but because of the factor theorem, oh my God, can you believe how money making the factor theorem is? But yeah, so the money, let me blow this up because they're going to go into a little bit of detail here. So the factor theorem says that if that we have the following factors of G of X. Well, if G of alpha is 0, that means, remember, that X minus alpha has to be a factor of G. And if G of alpha squared is going to be 0, we need that X minus alpha squared to be a factor of G, and so on up through X minus alpha to the delta minus 1. So the point is, so what this tells us is that what we want to do is we want to take these initial factors that we know we really want to have, x minus alpha times x minus alpha squared minus yada yada up through x minus alpha to the delta minus 1, and then somehow, I guess, add on other factors times be able to figure out what the other factors are to tack on and we want that to be equal to our g of x, so that somehow all this alpha stuff will cancel out in the way that leaves only zeros and ones as the coefficients of g. What? So, you know, I think if I asked you to do this sort of like straight away, this seems like, I would think this seems like a nearly impossible task. And so what happened, we're going to talk about for the next 10 minutes or the next 8 minutes, and then finish up on Wednesday is how to do this. Okay, so to do that, I need to talk about a few more facts about finite fields. So again, we want to think about, we're working with an extension E, which is f sub q, where q equals 2 to the little e. And this is actually why we've been using little e as our exponents, because that somehow relates to a big E. All right. Okay, so the first fact is not too bad. So if this capital E is a finite extension of f2, then beta is a root of x. Then the roots of this polynomial x squared minus x, which is x times x minus 1. If that's true, if beta is a root of that, if and only if beta is equal to 0 or 1. Well, that's not such a big deal, right? So that's that beta is a root of x squared minus x exactly when beta is 0, 1, because those are the only two roots of the equation. Because we solved the equation. There's a statement and proof of that part of the theorem. And 2, now this is a little more subtle. So rho is the squaring function. So let's define rho to be a function from e to e that squares every element. And so so the sort of much more subtle thing going on here is that rho is an automorphism of e. And in fact, rho fixes exactly, so the fixed elements of rho are exactly the only things whose squares are themselves 0 and 1, right? Because 0 squared equals 0, and 1 squared equals 1. And so certainly 0 and 1 square themselves to 1, and nothing else is squares to 1, because the u squared to 1, the only things that square to themselves are 0 and 1. And if anything else squared to itself, then x squared minus x would be equal to 0, and that'd be a root of this polynomial. So the interesting thing is that rho is an automorphism of E. So functions of that form, rho to the rho of beta equals beta squared, or in general, there's rho of beta equals beta to the q, beta to the p, are called Frobenius automorphisms. Or actually, more generally beta to the q. Okay, but here, we're only taking q equals 2, so great. All right, so I guess, what will I do? So let's prove that a Frobenius automorphism is a homomorphism. So in order to be an automorphism, you have to be from the ring to itself. So this is so automatically this is from E to itself. And to prove that that's an automorphism, we have to prove that it's a homomorphism and that it's bijective. That map rho has an inverse. So everybody should get ready to log into Canvas very soon, by the way. And so to prove, let me just to prove that Frobenius that squaring is an homomorphism, we want to prove first that rho of xy is equal to rho of x times rho of y. Right. This is the definition of homomorphism. You'll see that's not so bad. The surprising one is that rho of x plus y is equal to, this will take a while, rho of x plus, we'll take is a little more interesting. Rho of x plus rho of y. Now, rho of xy is equal to xy quantity squared. And because fields are commutative rings, this is equal to x squared times y squared. Look, that's equal to rho of x times rho of y. Great. So yay, that's done. Rho of x plus y, that's a little more involved. That's a little non-obvious because we somehow want, so rho of x plus y is equal to x plus y quantity squared. And you've been told many times that that's not equal to x squared plus y squared. Oh, no! Was it all a lie? Well, okay, yes, it is a lie because remember, x plus y quantity squared is equal to x squared plus 2xy plus y squared. And remember, we're working in characteristic 2. So because our sort of base field is F2, we're working in characteristic 2, and so 2 is equal to 0. And so, yes, this is actually true. So finally, your dreams have been realized. That's finally the case that x plus y quantity squared is equal to x squared plus y squared, except that, well, on the minus side, this is somehow wrapped up into some complicated thing called a Frobenius automorphism. On the plus side, you can actually use the fact that this is finally true to make money. All right. Anyway, so there, and actually, for those of you who may be having a little trouble with the homework where you prove something as homomorphism, this is how you prove something as a homomorphism. Okay, 3 minutes until we do our upload test. Maybe 1 more minute of talking. And right, so so this is how you prove that a map is a homomorphism. You have rho of xy equals rho of x times rho of y, and rho of x plus y is equal to rho of x plus rho of y. Okay, I think right. So I want to. Let me just mention this one last definition. The minimal polynomial of some element beta of an extension E over F2 is the what is it? It's the m of x is the smallest degree polynomial that has beta as a root. I mean, that's more or less what this says. And so next time we'll see how to compute m of x using Frobenius automorphisms. What? How complicated? Okay, so that's where we'll end our talking for today. All right, so bye YouTube. So I'm going to stop the recording.